Hi, in this video, we want to take a look at feature selection for logistic regression models. Okay, so feature selection is where after I have my data accumulated and after I've done my feature engineering, I'm going to choose what's actually going to be in my model. All right, so what's going to end up happening when I'm doing a real life model is that I'm going to have a large collection of potential predictor variables. And some of them I should keep, some of them I should kick out. Some of them I should actually go back and do some feature engineering on, modify and change. All right, so the feature selection process, what we're going to do, we're going to decide what do we keep, what do we get rid of. All right, so the number one thing that I'm going to have to consider with this is my project. What do my stakeholders want? I've personally been in this situation where my model had to have predictor variables because of legal constraints and because I needed to make sure that I could not have a legal challenge to my model. Somebody in an academic paper said that these predictor variables were important, and to make sure that my model wasn't like Swiss cheese for legal scrutiny, I had to include predictor variables that I personally would have kicked out. But it was still a decent model every single time I did this. Now, first thing is my project, so my stakeholders. What do my stakeholders want in the model? Guaranteed. So you're going to be in the situation where your stakeholders absolutely insist on these particular predictor variables have to be in your model, and you include those, right? I'm doing the project for them. That's what's most important. Our number one goal in this is to get my stakeholders to believe in my model 100%. If they don't believe in the model, even though it's statistically solid, it's great predictions. If they don't trust it, they don't believe in it, they're going to kick it to the curb, and all my work was for nothing. And now, one approach would be like, hey, I want the best model possible. I'm going to take every single predictor variable and throw it in to one big pot. Well, what's going to end up happening is that's going to be like too many cooks ruin the soup. All right, so by having predictor variables that are redundant with each other, I'm actually going to get a worse model than if I use fewer ones. And so my model performance is actually going to degrade if I have predictor variables that are redundant to other predictor variables. Also, it's going to be harder to interpret what's going on if I have correlated predictor variables. So imagine I had a predictor variable of height and shoe size in my data. All right, well, shoe size is correlated with height. And so there's kind of like a compounding effect on that. And interpretation is not going to be as direct because if I have like a fixed known height, well, that's going to influence the value of the shoe size, and that's going to influence the value of both of them together are going to influence the result of the target variable. And so it'll be confounded. It's hard to interpret. I'm better off by removing all the predictor variables I don't need. Also, if I have the more predictor variables I have, the more prone to overfitting I am. So there's always a difference between my training data and the target population I want to make predictions on. 100% guaranteed there is a difference. Overfitting is where I've done something where my model is detecting features in the training data that are not in the true population I want to make predictions on. Other thing I want to say, all models overfit. As to what degree do they overfit? The more predictor variables I have, the more prone to overfitting I am. And so by removing predictor variables, I'm less prone to overfit. So the reason for this is that if I have 2 or 3 or more highly correlated predictor variables, there's going to be just like kind of nuances in the data that just happen, and we model these as just like being random occurrences from a statistician point of view. And those little random nuances, if I have a whole bunch of predictor variables in there, can make it look like there's things going on in the model that are not actually true features of the population I'm trying to understand. And so I don't want to have redundant predictor variables. I want like an elite quality predictor variable. So, when we do feature selection, we're going for quality over quantity of predictor variables. Also, the more predictor variables I have, the longer it's going to take to compute. And, I don't know about you, but I like to not wait. And so everything will be faster, it'll be easier for us. we get our task done quicker if I have fewer predictor variables. This is going to be a big deal if I have to rebuild my model over and over and over, which is typical of a real life project. Typically, I go through, I build the model, we do things, we analyze it. I go back, change something, rebuild the model, look at it again, evaluate something, go and change something. I keep on going back to a previous stage of the project until we get something that we feel is very solid. It's almost never a one and done. All right, so now ways that we can go through and do feature selection. So typically what we have in a project is that I have a collection of predictor variables that I have before I do my model fitting. And we've reached, like, we've talked to our stakeholders, we've worked with our data engineers to get as many predictor variables as possible that are relevant. And so the first thing we're going to talk about, well, is going to be what my stakeholders want. Whatever my stakeholders want, that's going in 100% guaranteed. Now, after that, I still have a bunch of predictor variables that I may or may not include in my model. And we're going to go through and just decide what to keep, what to get rid of. So one thing is going to be a filter method. So here, the idea is I'm going to look at the correlation or the chi-square test, or I'll look at the relationship between the predictor variable and the target variable and the predictor variables with other predictor variables to decide, should I keep this, yes or no? And typically what we do is that we start with a big list and we start whittling it down until we get down to the model that we actually want to use. So at each step, we basically kick out a few predictor variables, and we keep on analyzing and reevaluating as we progressively go. Now, wrapper methods, here we're letting an algorithm go through and do the feature selection for us. So here, think of like forward selection, backwards elimination. That what we're doing, we're telling the system to go in and build models and start kicking things out or bringing things in to make a better model for us than what we already have. Now, embedded methods, this is actually part of the model structure itself. There are certain models that will go in and actually do feature selection for us so we don't have to do it. Now, that sounds really attractive, that I wouldn't have to do any work, wouldn't have to fuss with anything. I just, run Lasso. Trust me, you want to do manual feature selection first. You don't want to just take everything, dump it in a Lasso and say, hey, it's good. It's going to end up that, if I have like two correlated predictor variables from subject matter knowledge and you're working through things, you might know that one of these is better than the other. And Lasso would take the lesser of the two if you ran it. So what you want to do, you want to manually get rid of things and then proceed forward. Now, I didn't talk about here, but another thing we'll do is variable clustering to try and identify which predictor variables are redundant with others so that I can identify what to remove. All right, so let's go ahead and set up our workspace. I'm going to be using piping. I'm suppressing the number of digits printed, and I'm avoiding scientific notation. And once again, I'm going to use the SA Heart dataset from elementary statistical learning. And so this has chronic heart disease in here. And I'm going to convert family history to its dummy variable version. And so now right now, I'm going to build a model. I call it the full model with all predictor variables, because we're going to do feature selection in a moment. So here, this is with everything just thrown in. I'm not worrying about variable quality on this model right here. All right, so I think that we're going to do, so I'm going to go through, I'm going to analyze my data. So, well, before I get to this point, I would talk to my stakeholders, see what they want, see what's important, and whatever is important to them, that is going in the model 100%. All the other predictor variables are a maybe at this point. All right, and what we're going to do, we're going to visualize the relationship between our target variable and our predictor variable to see, should it stay or should it go? Should we keep it? Should we pull it in? Or should we kick it to the curb? And I like to do this via visualizations. So to me, the best way to do this, if I have a binary target with a numeric predictor variable, I'm going to look at the box plots. A good predictor variable makes the box plots look like this. The boxes have a distinct difference. So the more of a difference in height between the boxes, the more likely I am to consider keeping it. All right, so here we can see that we have some in the vertical position. The boxes are overlapping, but the median bars are clear of the other box. So if I draw a line here visually, the median is above the box. Here, the median is below the other box. So I would accept this initially for this. And a lot of times we end up just kind of like noting this and using this through the process of eliminating later down the road. Now here I see that the median, if it's not clipping the other box, it's close to it. I would be less prone to using tobacco in the model than the previous one. All right, now here I've got the line cutting through the other one. So now I'm feeling less strong about adipose tissue. Maybe I'll keep it, maybe I won't. But as I go through this process, I'm getting insight into what's going on. I'm getting an idea of what should be kicked out first and what should be kept, brought into the model first. All right, we can see that it's going into the box, So I'm not really feeling too great about cholesterol. Maybe I keep it, maybe I don't. So here, systolic blood pressure, maybe I keep it, maybe I don't. We'll go through. Type A, like I would, right now I'm prone to removing type A off of this plot. And same thing with obesity. Now here's alcohol. So nothing's really like that strong on this. And by going through this process and doing the visualizations, I have an idea of what is going to be the best to remove as I go through and start trimming out the predictor variables for my model. All right, now here, when I have categorical predictor variables, what we're going to do, we're going to look at bar plots. And there's a million different ways, not million, but there are a bunch of different ways to present this that make a lot of sense. Here I'm using bar plots. What I want to see, ideally, would be that when I have one level of the predictor variable, I see all heart disease or no heart disease. And on the other level, I would see the exact opposite. That would be the ideal situation. So what I would like to see would be like this bar would have 90% heart disease, or let's say 99% heart disease. This bar would have 99% no heart disease, something like that. That would be a good predictor variable for us. All right, another way that we can approach this is that since I have two levels for my target variable, to help me decide if I'm going to use a numeric predictor variable, I can actually run a test to see if we have the same central tendency. Now here I'm running a t-test. Potentially I could have done a z-test, which statisticians almost never actually use, even though it's a big part of introductory statistics. Or I could have used Wilcoxon rank sum test, anything like that, or a sign test to see, do I have a different central tendency? A large difference in central tendency is an indication that I should probably keep that predictor variable in my model. And so that would result in a small p-value for a t-test. And so here are the p-values for this. And so a small p-value is an indication that it should be in the model. A larger p-value is an indication it should not be. So here, like alcohol would be the one that I would be prone to removing first off of this metric, this approach. Age would be the one I would want to keep the most. So let's look at the box plots of age and alcohol. So here's alcohol. The boxes are looking really similar to each other. Really, they're almost identical. Let's find age. All right, and age is the one that had the most different boxes in terms of their vertical position. And so here, this confirms that age would be a very valuable predictor variable. Now we can also do the non-parametric test. And so here I'm using Wilcoxon rank sum test. And once again, by this measurement, we see that age is the one we want the most. By this measurement, alcohol would be the one we would be most prone to removing. Now, we can also do a chi-square test. Either we can bin our numeric predictor variables and do a chi-square test, or we could just use this with our categorical predictor variables. Either way works. There's a way to convert the chi-square test statistic into like a correlation, but I prefer to actually use a test. Either way, I've got coworkers that like to modify this to get it that way. All right, now another option we have is correlation, even though I'm doing logistic regression. All right, when I have a large data set, some of these computations can take a long time and they'd be hard to run. And a way that's actually pretty fast correlation, Pearson correlation is pretty quick to compute. Now, I'm not using Spearmans, I'm not talking about Kindles, but if I was to pretend that my binary target was a 0 and 1 vector, and then run correlation with a numeric predictor variable or a binary predictor variable, Pearson's correlation is pretty fast. And so sometimes when I have trouble with memory or computation time, issues like that, using Pearson's correlation is a way to get around it. Now, from a theoretical point of view, never tell a theoretical, classically trained statistician that you've done this. They will have an aneurysm. It'll be ugly what happens. So they will, like, their head will explode or something. This is theoretically the incorrect way to go, but if I'm in a big data set, it's not a great way to go. Also, this is good for stakeholders who don't have a strong statistics background. If they don't have a strong statistics background, they probably have at least heard correlation. And what you always want to do, you want to give justification that your audience is prone to accept, prone to receive. And so if I have stakeholders with like an education background or maybe a psychology background, they're going to know correlation. And I can say, here is the correlation between the two variables. And usually they'll accept it, not knowing anything else. If I was going to present at a statistician conference, I absolutely would not use Pearson correlation with a binary target variable. And so here, once again, if I sort the correlations, we can see that age is the one that's coming out on top, while alcohol I would be prone to removing. All right, now something else we can do is that we can start with the initial model and then start comparing different combinations of models. And we can use Akaike's information criteria, Bayesian information criteria. We can also modify the formulas. And what's going on here is that we can take the log of the likelihood for the model and then have a penalty term. And here's the log likelihood aspect, and here is the penalty term. So in Bayesian information criterion, the penalty is the number of parameters times the log of observations. And here, the penalty for Akaike's information criterion is number of parameters times 2. Okay, so we want the smallest AIC or smallest BIC possible. Now, when I look at AIC, BIC, if I have two different models, like two different data sets, I can't compare them. So AIC and BIC, we use this to compare models on the same data set. All right, and so we want the smallest value possible. Either way, BIC will usually, it will favor smaller, simpler models. They'll favor kicking out predictor variables that AIC would not. So we can use this in forward selection. And so forward selection, what it's going to do, it's going to start with just the intercept. It's going to look at which one predictor variable should I add to only the intercept model. And then I have a one predictor variable model. Now, it's going to take these two and it's going to say, hey, which one predictor variable would be the best to add to this to get two predictor variables? And then it keeps on going until it hits the point where it can't improve the model by adding things in. The criteria that we typically use is either AIC or BIC, but we can also modify it. And honestly, we could go with other criteria, but most often we use AIC or BIC. No, backwards elimination starts with all predictor variables in the model, and it finds which one would be the best to remove, and it keeps on doing that until we would not improve the model by removing predictor variables. And don't be surprised if you get slightly different models. Notice I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 predictor variables. Here I have 1, 2, 3, 4, 5. I have 5. And you'll notice that I've got, so both of these are BIC. And so if I do forward selection, backwards elimination, or forward back, I'm going to typically get a different model. Which one's best is a subjective call. And forward back this one looks like it's the same as backwards elimination. Now, Lasso, this is the least absolute shrinkage and selection operator. What this is going to do is that this is going to apply a penalty term to evaluating our model. And that penalty term is determined by a parameter times the sum of the absolute value of our coefficients. And so that penalty makes it so that the model would prefer to have smaller coefficients. And what Lasso does is Lasso is going to try to shrink down the coefficients to get a better fit off of this. And so this does a pretty good job. Now, if it shrinks it all the way down to 0, we interpret that as we no longer have that predictor variable in our model. So this does feature selection for us. And you'll notice that alcohol was kicked out of this model. And let's look up, and you'll notice that alcohol was kicked out here too. This includes age. Alcohol is gone, includes age. Alcohol was kept in forward selection, huh? That's interesting. All right, well, for your homework, take your data, run feature selection, and just, look to see what it would be like to actually run feature selection in real life, get some practice doing it, hands-on, roll up your sleeves and do it, and then submit your results on Canvas. This is all I got for you. Life is short. Do math.